is quite expensive. So what do we do? Actually, it's not so bad because we can fix x, right? Because nobody said you have to generate, you can evaluate all the polynomials at the same set of points, right? Notice that x only depends on the points at which you evaluate, right? So you can fix x0 to xm, right? And you can say that for all multiplications, I'm going to use the exact x0 to xm. Therefore, this matrix can be computed once, and you never have to repeat that computation, right? Similarly, computing x inverse can also be done once, right?
Yeah.
And you never have to repeat it. So, yeah, go ahead.
So the matrix has, again, across rows n powers, and for columns,
Which column here? So this is point, the first point and its powers, right? The second point and its powers, third point and its powers.
has 2n squared entries, right?
This one?
Yeah.
This
So
one has
n is 2.
approximately n square entries,
Okay.
right? So it's within some, yeah, n square plus 2n or some, or n or something like that. Okay. So
And we choose the points arbitrarily.
we'll come back to that. Okay. So the point is that however you choose the points, you can keep them fixed regardless of which multiplication you're doing, right? So because of that, the complexity of computing x and x inverse itself is not part of the algorithm, right? Because it's already been computed, pre-computed, you store it forever, right? So, okay, at least that seems like that one we dodged, but then we still have to multiply the matrix x and a, right? So, because each time a changes, well, we have to do this multiplication, and still the matrix x has n square entries, and so there are going to be n square multiplications involved if you don't do this carefully, right? Once again, if you go back to this matrix computation, right? So multiplying these elements with this requires n multiplications, another n, and so on, right? So there are n square multiplications involved to compute this product. Wow, okay, so that means, you know, pre-computing x and x inverse isn't going to be enough. Okay? So now, then the main idea is that you choose the points so that you know you don't require expensive multiplications. Okay? So we'll see exactly how that happens. But let's say, for instance, if we choose to evaluate one of the points as 0, right? So you know that any polynomial evaluated at 0 will just give you a0, right? Because any other term, right? So if you have right? If you substitute x equal to 0, then all these terms will become 0. So you will just have a0, right? Which means that if you go back to this matrix again, what that means is that if you set x0 equal to 0, then all of these entries will be 0, and only this will be 1, right? So therefore, this whole thing, this row multiplied by this column, can be computed using one multiplication, right? So maybe there is a way to choose the points in such a way that a number of entries here will become 0, and therefore the number of multiplications we get is going to be small. Okay? So this is basically the idea of tune. Okay? So you're going to choose a point so that the multiplication x times a and x times b and x inverse times r, all of them involve a small number of multiplications, right? Not n squared, but a small number of multiplications. Okay? So, in fact, what you can show is that, no, I'm sorry. In fact, you choose the point so that there is actually no expansive multiplication. Okay, so in fact you don't spend, you only have to do addition but not multiplication. Okay, so the only multiplication comes up when you do the point-wise operations, right? So when after computing so the idea is that computing P and Q, you're going to choose X in such a way that computing P and computing Q essentially involves only addition. Okay, it doesn't involve any multiplication. And therefore, the only multiplications you need to do are these. Okay, so you got to do M multiplications. And we said before, M is going to be something like 2M. Right? So coming back, so we are going to do 2n minus 1 actually, right? So it's not exactly 2n, you need to do 2n minus 1 multiplications. Okay, so let's understand this recurrence a little bit more carefully. Now let's peel the next layer of the tomb algorithm. Okay, so the next layer is that if you think of an n-digit number, right, we refer to digits either in binary digits or decimal digits, right? So those are the base number. The bases that we often use are either the binary base or the decimal base, right? But Tomb and Karatsuba and so on work with very large bases. Okay? So what is this very large base? So what we are going to do is right. So in the case of Karatsuba, right, we divided an n-bit number into 2 parts, right? And then we treated. Let's go back to the Karatsuba, and then we'll see what we are doing here. Right. So we took an n-bit number and divided it into 2 parts, right? So this is like a 2-digit number with the base 2 to the power n by 2, right? It's an n-bit number. If you divide it into, if you slice it right in the middle, then you can think of them as 2 digits in a very large base, where the base is 2 to the power n by 2. Okay? So what we are going to do in the tomb algorithm is we are going to divide a number not into necessarily 2 parts, but capital N parts. Okay? Yeah. So we are going to take an n-bit number, right, and divide it into, a tomb has a parameter n, right? Tomb n will divide the input number into capital N parts. Okay? So think of it as a number which is represented using capital N digits, right? And each of those digits, of course, is very large. So if you're talking about, let's say, 1500-bit number, and let's say you're doing tomb 3, right? So then you are going to divide this 1500-bit number into 3 digits, which means that each digit corresponds to 500 bits, or the base is 2 to the power 500, right? So that's what we're going to do. So that is the capital N, okay? So in the example I gave you, N is 1500, the lowercase n is 1500, capital N is 3, right? Tomb 3 operating on 1500 bits numbers will first break it into 3 500-bit parts and then go from there, okay? Now, because you see that we said that the only place we will design somehow magically pick the points x0 to xn such that there are no multiplications involved here. So the only multiplications are involved here, which means that we have m multiplications, right? And we said m should be 2n minus 1, right? So again, so the number of points, right? So if you want to think of it as a capital N digit number, right? Then we need capital N times 2 plus 1, right? That many points we need to work with. Because again, if you have capital N digits, that means we have a polynomial whose degree is capital N, right? And what we said before is if you want to do this, all this without any loss, then the capital you need to work with, 2n minus 1, 2 times capital N minus 1 points, okay? So your m in the previous slide is going to be 2 times capital N plus 1, which means that you basically are doing 2n minus 1 multiplications, okay? Now, after that, you will be left with multiplications involving digits, each of them being much smaller, right? The example I gave you, capital N was 3, small n was 1500, right? So we have something like t of 1500 equals 2 capital N, right? So two times capital N, which was 3, right? Minus 1 times t of 500, right? Because we have broken up an n-bit number into capital N parts, which means that you have divided the problem into many smaller instances. And then, yes, you have these additions that you still have to perform, and so those additions will cost order of n time, okay, to do this, to combine, right, all of the results of the digit-wise multiplication. You have to do some number of additions, so we will add an order n for that, okay? And this is a nice, recurrence that fits the master theorem, right? So we ask the master theorem what is the answer, and the answer is n to the power log n to 2n minus 1, okay? So now notice that this can be as small as you want, right? It is going to be greater than 1, but it can be arbitrarily close to 1 if you keep increasing the value of capital N, right? So for instance, if let's say capital N is 2, right? So this one will be log base 2, this will be 3, okay? So if you recall the Karatsuba algorithm's complexity, it's exactly n to the power log base 2 to 3, right? So Karatsuba, which is tomb 2, right, or rather tomb with n equal to 2, gives you that complexity that we talked about before. But you can improve it by setting n equals, let's say, 4, right? If this is 4, this will be 7, right? Log of 7 to the base 4 is much smaller than 2, right? Because 4 square, right, is 16, right? So what you have here is 7, right? So 16, if you get to 16, then the log will be 2, but you're only at 7, so the log should be much smaller than 2. So you get much closer to 1, and if you set it to some relatively high number like 1000, then it will be very close to 1, okay? So the Tomb-Cook algorithm is a general algorithm that allows you to reduce the complexity to be almost linear. So okay, so we'll come back to that, but before that I want to sort of illustrate the Karatsuba algorithm again using the point-wise representation that we discussed, okay? So we are going to evaluate, you're going to choose 3 points, which are 0, 1, and infinity, okay? We understand how to evaluate it at 0, right? So if you evaluate it at 0, it should just retain A0, right? So if you evaluate it at 0, we already said that if you want to evaluate at 0, then that row will consist of 1 in the first column, and then everything else will be 0, right? Because this is x to the power 0, x to the power 1, x to the power 2, right? So 0 power 1 is 0, 0 power 2 is 0. Similarly, this is 1 to the power 0, 1 to the power 1, 1 to the power 2, right? So all that is fine. This is the only special case because it's infinity. So what is the meaning of evaluating something at infinity? Well, instead of just saying that this is, when you evaluate a polynomial at infinity, it yields infinity, we are going to, redefine it to be the value of the largest coefficient. Okay? So because the idea is that instead of just saying infinity, let's compute the limit of a of x by x to the power right. Instead of just evaluating the polynomial outright, which will just give you infinity, which is a meaningless result. Instead, for the case of infinity, we just define the value to be something like this. Okay, so we have a special treatment for the case of infinity, and as long as you do this consistently, right, for all polynomials, it should be fine. Okay, so that's what we are going to do, which means that I'm going to just pick the most significant coefficient because that's the only thing that's going to matter. So 0, 1, 0, right? So now, again, I take powers of 0, put it here, powers of 1, put it here, and powers of infinity, if you want to think of it that way, there, and then this is what my x is, and then you compute x times a, right? And that gives you a0 plus a1 and a1. Okay. Similarly, xb is the same kind of computation, so it should give you b0, b0 plus b1 and b1. And now when you do the pointwise multiplication, you should get these 3 points, right? And if you go back and look at what was that trick in Karatsuba to reduce the 3 multiplications into 2, well, that involved doing this multiplication instead of these 2 multiplications, right? So when you reduce it to 3 multiplications, we do the a1, b1, we do a0, b0, and then we do a1 plus a0 times b1 plus b0, right? So this magically happens here, right? So we didn't have to do anything. We just did this, mindless thing of evaluating it at some points and doing a pointwise product, and that ended up automatically picking the right things to multiply. Okay, and if you go through the, if you compute the x inverse and do the final step, you will see that the rest of the Karatsuba algorithm also, drops out, right? It'll fall out of this. I'm not going to spend that. I'll just leave it as an exercise for you to do, right? Because that way it'll force you to understand exactly what's going on, right? Any questions? Again, what you need to understand is you have to understand this in layers, right? So we see the correspondence between polynomials and integer representations. Once we have polynomials, then we can think of them as curves, and once you have curves, then you can, define them by identifying points on the curve, right? And once you have points on the curve, then you can start saying, oh, when I want to do addition or multiplication, I can just take these points and do operations involving the points in a pairwise way. And now by either adding the points pairwise or multiplying the points pairwise, I can compute the product. So now I have computed this product, 2 endpoints on a product curve. And once I have the 2 endpoints on the product curve, I should be able to uniquely identify what is the curve at that point. And that is what we did, right? And now we needed to choose all these points in a careful way so that in the end, we will be able to do all of this quite efficiently, okay? So now, in the last slide, I said that you can make this to be, the complexity can be reduced to something like n to the power 1 plus epsilon for arbitrarily small epsilon, right? And but the problem is that the algorithm itself depends on the choice of capital N, right? Because you have to do a lot of additions. If you choose n points, then you have to do corresponding number of additions, right? And also once the matrices become large, the operations involved will become more complex, right? So that's why when you increase the matrix to 4, you already have a 16 element matrix to work with. So there can be a number of operations, even if they are not multiplication, they are still a number of operations. And by the time you increase it to maybe 25, the constant involved in your algorithm rapidly shoots up. As a result, TOOM is generally not used beyond n equal to 4 or 5. Okay. So before I go back, right? So let's make sure that we understand one point here, right? So Karatsuba as well as TOOM are all divide and conquer algorithms, which means that after you're going to do all of this, right? But in order to do this point-wise product, right? Again, in the example, right, we had 1500-bit numbers, and in working out that product, we will be doing products of 500-bit numbers, right? So these 500-bit numbers, once again, we'll apply the same algorithm recursively, right? So when you apply that, then that 500-bit number will get divided into 167 bits, right? 167-bit numbers, right? So now you'll have point-wise products involving 167-bit numbers. Then you'll recursively apply that, and now it will become 56 bits. And you keep doing that until you get to a small enough number. So for instance, if you get to 56 bits, then it already fits within a 64-bit width of a typical processor, and therefore you certainly wouldn't go below that. Okay. In practice, you probably will stop at a few hundred bits, and at a few hundred bits, you probably will do the expensive n-square type of multiplication, because even at, let's say, 128 bits, right? If you want to do 128 bits using the naive algorithm, it just involves 4 multiplications on 64-bit values, right? So this is quite, much faster than trying to, run any of these algorithms, right? So in practice, by the time it gets to a few hundred bits, you're not going to use these fancy algorithms, right? So they are really useful when you have 1,000 bits or more. Okay, so again, don't lose sight of the fact that although we just described one level of the algorithm, it's a divide and conquer algorithm, so it's going to be recursively applied at each multiple levels, right? We just understand what is one sort of iteration of this algorithm involves. Okay, so now that is the limitation of TOOM. So in practice, n equal to 4 or 5 is where you stop. I'm not even sure who uses n equal to 5. Right, so n equal to 4 could be, in fact, where people stop. Okay, so can we go forward? Okay, so then there is even more interesting algorithm called Schanhage-Strassen algorithm, which we will very quickly try to understand. Right. So again, maybe understand is not the right word. We will try to get a flavor for what it does, right? So because it's, again, based on this polynomial representation, okay? And so what we want to do is we simply want to say, okay, is there some other way, right, to look at this problem so that we can get better complexity, better asymptotic complexity than TOOM algorithms, okay? So the idea is the following. Okay, so let's take this, right? Now, the reason why this operation is expensive is because we do this evaluation independently for each value of the point, right? So for x0 we do the evaluation, for x1 we do the evaluation, for x2 we do the evaluation, and so on, right? So this is what is expensive. So the idea is that can we have and in the case of TUM algorithms, there was magic, right? So by magic we chose certain points where the evaluation was easy, right? Remember what we said in the TUM algorithms is that all this whole thing has no multiplication, right? This whole product computation doesn't involve any multiplications. Okay, so we did that somehow magically, and in fact, it doesn't even involve too many additions, because even if you say it involves each of them requires n additions, that's too much because there will be n square additions and you're dead, right? So somehow we chose in TUM points such that we will somehow get this all done in just order of n operations. So now the question is, but that was quite difficult because for n equal to 2, we had a particular way of defining points. For n equal to 3, there is a different set of points. If you look up the TUM algorithms, right, you'll see that there is a different matrix and different set of points at which you evaluate. There are some commonalities, but in general, things get complicated. And you'll see the complication even when n equal to 3, right? It just becomes too difficult. What if I want to make n to be 1,000? Well, that's not going to work, right? So the question is there a more systematic approach one can use to make things easier? So I'll just try to give you a very high-level idea of what is going on. Okay, suppose you know that you are evaluated at, let's say, 2 endpoints. Okay, suppose you evaluate it at x equal to 1 and x equal to -1, right? So at x equal to 1, the value of the polynomial is going to be okay, so I have divided it up into odd coefficients and even coefficients for the reason will become obvious later. But clearly, when I substitute x equal to 1, all of the terms will just reduce to their coefficient, right? So if I have 5x squared plus 7x plus 2, and I want to evaluate this at x equal to 1, then all of these I can just remove, and then it will become 5 plus 7 plus 2. Right? So that's what I have done here. I have said, okay, the value of the polynomial at x equal to 1 is simply the sum of all the coefficients. Right? At x equal to -1, right, what's going to happen is that in this case, if I evaluate it -1, then this will become 5 minus 7 plus 2. Right? So what is going to happen is that the even terms will remain as they are, a0 plus a2 plus a4, okay, and then right, see, all the odd terms will become negative, the even terms will remain positive, right? So you can see that now by choosing sort of matched points, that is, one is the negative of the other, right? I'm able to share the computation, right? So essentially, instead of computing this twice, right, I don't have to compute this sum twice, right? Because I computed once, and I can reuse the results for both, right? So the idea is that somehow, instead of doing n additions, I have reduced it to n by 2 additions. And you can actually convince yourself that I can do this for x equal to 1, 2, minus 2, right? So if I did it for x equal to 2 and minus 2, so what's going to happen? This is going to be 2 power 0, 2 square, 2 power 4 times. But the exact same thing is going to happen here, right? Yeah. So even though it's no longer a2, it is 4 times a2. But this exact same thing is going to happen here because I have minus 2 here, right? So the same kind of sharing is going to be applicable even if it's something other than 1, right? So what that tells you is that by evaluating it, choosing the point so that you have positives and negatives of the same value, you can compute this once and share for the other half, which means that if you have 2 endpoints, right, you only have to compute this only for the positive points, which means that instead of doing 2 n computations, you will do n computations. Okay? So this is good. But unfortunately, what happens is that this trick seems to run out. It seems like you can apply it only once, right? In the sense that if you want to do it as a divide and conquer, right? What you have done here is you said, I'm going to take this 2 endpoints, I'm going to cut it into half, right? And I only compute half for half of the points, right? So that'll give you twice the savings. But if you want to get any asymptotic savings, you have to do this recursively again and again, right? Which means that somehow, in computing this partial sum, somehow you need to again, get this kind of, ability to share the computation. Okay.